Today we're going to do k-means. The name sounds very similar, but they're very different. The only similar thing is that they're both using distances, the concept of distances for machine learning, and that's about it. Okay? But let's talk about KNN briefly. So what is KNN? Well, you have your training set. Let's say this is class 1, and let's say there's a class 2. And for KNN, there is no training. The training sets themselves are already the ones that you use to classify. So suppose you have a new item here, somewhere here. Okay. Then, well, it's it has to be closer to 1 here. Suppose you're here. Okay. Then what you do is you look for, say, if k is 3, then k equals to 3 KNN would select 3 nearest points. That doesn't look right. I think it's more like this, maybe. Yeah. And then say that, oh, since among the nearest points there are more x's than dots, so this new point must belong to the x group. That's the concept of KNN. Okay. Notice that a priori, somebody has to make a training set saying that, oh, these are the dots and these are the x's. Okay? Yeah. So what we're doing so far are we were working with labeled data where the features are given but also the labels were given. Right? But sometimes you might not have labels, and you have to either do it on your own or hopefully make the machine figure it out on its own. Okay? When you try to make the machine figure out on its own, that's called unsupervised learning. So let's think about this situation. You have similar looking data sets, but like this, but none of them are labeled. And then the question is, what kind of data are there? That's the kind of question you can ask, right? So, in other words, if you have k-means, you have your data as not labeled, and you have to figure out what kind of groups there may are. Okay, and I think looking at this data, for humans, they naturally would say, oh, that would be like 2 clusters, right? Do you agree? There's 1 cluster here, there's 1 cluster here, right? So you would name this as 0 and this as 1, or 1 and 2, something like that. Is that okay? And then this one, if you had a third group somewhere here, you would easily see, even without any labels, you would say this is the third one. So unsupervised learning algorithms, there are some other completely different types out there, but in most cases, a lot of the unsupervised learning are clustering algorithms. Okay. There's another type where in deep neural network, you could also try to predict without having to do, well, okay. So when you say unsupervised learning, I guess there are basically 2 things. One is clustering, just like this. Another one is PCA. We've done PCA, right? So I said we never did any unsupervised one, but PCA is another such thing. So when you do PCA, you don't need a labeled data. You just among like hundreds of features, you select 3 most prevalent ones or 10 most prevalent ones, and what you're doing is you're doing dimensionality reduction. Okay, so. So there are basically 2 types of unsupervised learning: clustering and dimensionality reduction. Okay? Now, the next thing that you have to know in both cases, we already discussed distances, but the 2 mainly used ones are the usual Euclidean distance. So distances are measured by 1, and number 2, there's something called Manhattan distance, and there are some more ones, but these are the 2 that you definitely need to know. Euclidean distance is just that. You just take the square root of sum of differences of features, right? So that's Euclidean distance. For Manhattan distance, it's the absolute value of differences added up. So for example, if your feature set was 3, if you had 3 coordinate systems, say 3, 1, 1, and then 0, 2, 2, the Euclidean distance would be 3 minus 0, 1 minus 2, 1 minus 2. So it will be 9 plus 1 plus 1, square root of 11 will be the Euclidean distance between them. Whereas the Manhattan distance will be 3 minus 0, 1 minus 2, 1 minus 2. So you're going to get 3 plus 1, which is 5. Okay. You have different ways of figuring out the distance. Manhattan distance is often used for if your data set has a lot of binary type dummy variables. So it's like rather than numerical values, if you have male, female, or what else? Color, blue and red. So if you have those kind of binary type data in your data set, then you would it's often preferable to use Manhattan distance. Euclidean distance is used when you have a lot of numerical data. But here's another problem. In both cases, when you're calculating either Euclidean or Manhattan distance, you're assuming that the feature sets are measuring something similar. At least you want them to have the same units. So for example, if you had a group of people where you had height and weight, and let's say you're using this data to predict how much blood cholesterol the person would have or something like that, then you have certain points. Then when you measure this distance, the value of the distance will change dramatically if you work with the centimeter kilogram system for the height and weight, or if you use inches and pound system, because they would the scales will be different, right? So you will get different values for here. So when you have different units, these distances will be sensitive to the units, and therefore, before you take these distances, it's advised to make these things unitless by dividing by their standard deviation. Okay? So you all know of the z-score, right? What's the z-score? Z-score is you take any value, subtract the mean, and divide it by the standard deviation, right? If you do that, then this quantity z-score is always dimensionless. So doing this kind of transform before feeding into k-means or k-n would be advised. Okay. In the scikit-learn, there's another type where they just simply take not the z-score, but they call it whitening score, which is just simply divide the value by standard deviation. And because subtracting a common value just shifts the data and doesn't change the distances between the points, this extra calculation is not really needed. So this process of dividing the value by the standard deviation is called whitening, coming from white noise, but there is a whiten command you can use from SciPy that can be used for exactly that purpose. Okay, so now let's think about how the k-means would work. So suppose you have this cluster given. How are you going to say that, oh, there's this one group of cluster, there's one cluster here, there's another cluster here, and I think this should be two clusters. Okay? How would you do that? Well, the way the k-means algorithm works is by following the first step. Number one, randomly choose k points, k data points. Okay? So let's say you chose this one here and say this one here. Okay? Then what you do is cluster or classify using nearest points. So what I mean is that, let's use a circle for this one. So for this point is closer to the star than the circle, right? So this is going to be classified as a star. This one too, star, star. And basically, you can think about the perpendicular bisector somewhere here, so that this one will be a circle, and then the ones on this side will be stars, right? And these will be circles. So you do this, and of course this is not the correct clustering, right? So you have to do this procedure again. But what's the third step? Third step is compute the centroids of each cluster. Okay? Then go to 2.
Thank you.
Okay? Go to step 2. So you just keep doing this over and over, okay? Until this process cannot be improved anymore. But what does it mean to be improved? That I'll tell you later, okay? But so let's see how this third step would go. So here, with 1, 2, 3, 4, 5, 6, 7 points, there is something called the centroid, which is just simply taking all the x coordinates and the y coordinates, or if you have more than 2 feature sets, then it might have like it's a vector, right? If you have any data that you have to classify, these are vector of data, right? Vector of features. So those features are numbers, so therefore you can calculate the average of all the x values, all the y values, all the z coordinates and the next coordinates and all that, and that's going to give you a center of that. Okay, okay, that's called the centroid. Okay, and this one will also give you some kind of a center here, right? Now with these two centers given, right, and then if you start classifying using these two centers, then this point which was misclassified is now closer to this one than that one, right? Because if you have these two centers taking the perpendicular bisector, you see that this is now correctly classified. Okay? And then if you do the process again, then the centroids will be moved, but I don't think it's going to change any of the classification. Is that okay? So you just keep doing this. That's how the K-means algorithm works. It's pretty simple, right? Yeah. It's pretty simple, but because you have to do this over and over again, and you have to compute distances every time, this is a very long process. So it's not a very algorithmically optimal kind of thing. It takes a long time if you have a big data set. So if you have a very big data set, K-means might take very long time to do it. Okay. Now, I talked about measuring how effective this clustering is. And there are two ways to measure the effectiveness of a clustering. So first one is called the distortion. And the distortion score is simply, it's a sum of all distances, or could be averages, in each cluster to its centroid. It's centroid that was used for classification. So at this moment right here, the distance between each point to the centroid, that's the distortion. Okay? And of course, if you think about the one step before, one iteration before, when this was misclassified, you would have this kind of distance, which is quite big, so that what you know is that if you take sum of all the distances like that, or if you take the average of all the distances, then the value will go down, right? The values of the sum of the distance will go down as you iterate, right? So this procedure that you iterate will always make the distortion go down and down and down. Now, there are no agreed upon values. So SciPy, I think, does sum of all the distances, or maybe it's the average, I can't remember. But in a lot of literatures, they have square of the distances as the distortion. It doesn't matter, it's still the same concept. You want the distances to be minimized when you have these clustering. And eventually, if you repeat this process, because it's the sum of distances, it has a lower bound, right? You can't have distances adding up to negative number, right? So always go down, but at some point, it's not going to be any more improved by switching these centroid points, right? So at some point, this is going to terminate. Okay? That's how this algorithm knows when to stop. Okay. Now there's a second method of measuring how good the classification is, and this one is not used for terminating the algorithm, but it's a very good way to figure out if your classification is doing a good job. So, the next thing that I want to show is the silhouette score. And the silhouette score is given by first introducing AI and BI. Okay. So AI is the, for each point, so let's say I is a point. For ith point in your data set, so just pick one, okay? So pick any point in the data set. And then AI is the distance, maximum of the distance from that point to any other point in that same cluster. So max distance within cluster. Okay. And then BI is closest distance from the other cluster. So this is the minimum distance from another cluster. So if you had 3 different clusters, so let's say you have something here, another one, but then this distance is closer than this one, so this will be your BI rather than this one. So here, this distance will be AI, this distance will be BI. Okay. Okay. And then the silhouette score S is defined as the so in this case it's BI minus SI. Something wasn't right. BI minus AI, BI minus AI, and 1 minus AI over BI, BI over AI minus 1. Okay, so I made a mistake of switching these two around, so something didn't add up. But still, it's true that the values are between -1 and 1. So let's look at this. If I define the silhouette score to be BI minus AI, and divided by the maximum of AI and BI, then think about the 2 cases, the case when BI is bigger and when AI is bigger. In both cases, the maximum of AI, BI can be separately calculated. In this case, BI is bigger, so denominator is BI. In this case, AI is bigger, so denominator is AI. And therefore, when you calculate this, you have 1 minus AI over BI. They're both positive, and BI is bigger than AI, so this is a value between 0 and 1. That's why it has to be positive in this case, but it also cannot be bigger than 1. This one, for the same reasoning, it should be bigger than -1 and less than 0, less or equal to 0. So we know that the silhouette scores for each point is a value between -1 and 1, and we're going to define the Silhouette score of the entire classification as average of SI. Now let's think about this case when you have a point that's close to other cluster and it's like far end of this part and this one's quite big. So in this case, AI is bigger than BI, so this is somewhat closer to this cluster. So in that case, this Silhouette score of this point will be negative. Does that make sense? Right. This value will be negative. But if you have something like any point, for most of the points, if it's clustered well, the picture is a bit hard to see, so let me draw this again. So let's say the K-means cluster succeeded in making these clusters. Okay? Then for this point, AI would be probably this one. That's the largest value, largest distance. Whereas BI would be this value. This is the closest one. And because BI is bigger than AI, if you subtract BI minus AI, it's going to be positive. Right? So if it's clustered well like that, then most of the values of the Silhouette score will be positive, or it might even be always positive. Okay? And therefore, since you're taking average values of positive values, your average Silhouette score will be something positive, close to 1. Right? And therefore, something like, if the Silhouette score is above 0.5, then you would say it's a good cluster. But that's just heuristics. Usually if you have a good clustering, you would have a Silhouette score above 0.5. Or even, some people even say 0.7. So some high value. And then if it's below 0.3, then it's not trusted. The cluster, that's just from experience. There's no mathematical theory behind why that would be a good clustering or bad clustering. But definitely, if your Silhouette score is negative, that means your clustering is very bad, because in that case, negatives will only appear when you have overlaps. Okay, so that's definitely bad. So something close to 0 or negative is a bad clustering score. If you follow the K-means, you'll always have a positive Silhouette score. You'll never get negative just because of the algorithm. Okay. Do you have any questions? Okay. So let me see if you understood the Silhouette score. So let me give you an example. Suppose you have 6 points, and let's say the distance between this one is 7, and that's 8, and then this distance is 11, and let's say this distance is 2, and then 3. So compute the what is the Silhouette score of, what's the Silhouette score of this black dot? Okay. Assuming that it's the classification is like that. What would you do? The one that's farthest away inside the same group would be 3, right? Minus what? The closest one to the other group, well, it's drawn as if this is closer, but I assigned 7 to this. Okay. So according to the numerics only, this is the closest one, so it's a 7. Right? Divided by what?
Why don't you use the 2?
I erased it, but the definition of formula is, sorry, I got it backwards, 7 minus 3. The formula is BI minus AI over max of AI BI, right? And the definition of AI is the largest value, the distance that is largest inside this group from that point. Okay, so this distance is 2, this distance is 3, so 3 is being used for this one. Okay, and then the definition of BI is the smallest distance from the other group. Okay, so this is 7. 7 is the closest one, so that's what you use. Right? Now, what do you divide this by? Max of AI BI. Which one is it?
7.
7 is bigger than 3, right? So you divide by 7. So 4 over 7 will be your silhouette score. Is that okay? Okay. So you do that for every point. You take the average. That gives you an idea of whether your K-means did a good job in clustering. All right. Now there is something still which needs to be figured out when you do the clustering. So in the demonstration that I prepared today, works with the iris data, and this one has 3 species. It has the sepal width, sepal length. There's a petal width, petal length. Four feature sets, and it's labeled as there are 3 different categories. Okay, so that's how this iris data is structured. So you're basically trying to cluster this in 4 dimensions. We have been doing this same question using either the logistic regression or the support vector classification. But what we're going to do is we're going to pretend that the label didn't exist. And if you are a startup company trying to use machine learning to do some stuff, this frequently happens because you don't have enough money. Labeling real-world data costs money because you have to ask some people to see it and put the labels. So long time ago, Amazon was putting huge amount of money labeling things, right? So they would have a product picture, and they would send it to some people in a country where the labor costs are cheap. They would ask the person to label it. Is this a picture of a kettle? Is this a picture of a frying pan? And they would label everything like that. Okay? And using that labeled data, you would be training the actual machines to see the image and actually figure out what kind of product it is. Okay? And for a big company like Amazon, who's working with many different vendors, they want to make sure that the products that they're selling is labeled correctly, right? So such a thing was pretty important back then. Now those are, some of them are public, some of them are still private. But you would have something like that. I mean, imagine that you're an archaeologist and you dig up something and you found a clay tablet and you have a bunch of letters. Right? How are you going to read it? The first thing you would do is to identify different characters, right? See which one is the same, which one's different. And being able to see the character and classify it as one type or the other, there will be something that humans could do, or a machine could do as well. Right? But that will be, if you do it by a machine, then there will be an unsupervised learning problem because it's not classified at all. Right? So imagine this. Let's say you're a botanist and you went into Amazon jungle and you found a bunch of iris, okay? And you measure their sepal width, sepal length, petal width, petal length. You also collected pictures and stuff like that, but then as you were coming back, you had a shipwreck or something. All the data is lost except for this. Now you want to come back with this data and figure out what kind of iris are there in that Amazon forest, right? And it's completely unlabeled now, okay? How are you going to figure that out? Ideally, you would expect that the data sets to have like 3 different groups. Now, you're going to see later when I actually plot it that the actual data doesn't come out like this. Unfortunately, some of them are very close. It's hard to see. But if the data was like this, then just by looking at it visually, you would say, oh, K must be equal to 3. I see 3 groups. And the K-means algorithm will be able to figure exactly which cluster should be right. That's good. But what if the data sets have this one group and the other one is close together? What happens then? Visually, it might look like 2, but maybe 3 could be right. You may even have forgotten how many different types you had. Maybe there are 4 different iris or 5 different. So now the question is, you have a question of what should be the appropriate K value. If you're truly doing an unsupervised learning, if you don't have any idea of how many clusters that you're looking for, then this question becomes another issue, right? So let me try to explain how to find it out. Okay? So one way to do this is to draw the graph of the distortion. So what you get is you have for K equals to 2, 3, 4. So for different values of K's, you can do the K-means clustering, and each of these will give you the distortion value, right? And as I've noted, you're going to get values that are going down, right? Because distortions will always go down as you increase your K values. And then at some point you're going to find something that's called a knee. So this point right here is called a knee because the value of the distortion was dropping rapidly, but after some time it does drop, but it doesn't drop that much. Okay? If that happens, that's called a knee, and people say, well, that's like a good point an ideal value of the K to pick. Right? Except the problem here is that a lot of times the knee might not be so visible. You might just have simply something that's smoothly going down, so you really can't determine where that point is. So this is like one way. Another way to figure out K would be to use the silhouette score. Where you take, you calculate the average silhouette score, and the problem, the silhouette score is made in a way that it doesn't necessarily have to go down. It may go down, but it doesn't have to be. I think eventually when you increase silhouette score to something really large, it eventually does get close to 0 just because the difference between groups and then inside groups, their differences become quite small. Yes?
When you use a distortion and you find the need for your K value, does it tell you which specific points are in that K value, or it only tells you how many groups there are?
It only tells you how many groups there are. The K value, so this is a way to find the K value. Okay. Oh, there's another thing that I forgot to mention. If your data is not clearly classified, then this this iteration of the k-means algorithm, it may converge to different values depending on your starting point. So I said in step 1 of the k-means, you pick random values, right? So if you have some random values picked and your data is not really classifiable with that k-value, then it's just going to converge to some place where it depends on your initial chosen point. So even if you know the knee and you're using the k-nearest neighborhoods to figure out the value of these distortion, every time you run it again, the values of the distortion might be slightly different. It's not always the same. Okay? And your classified points will be also different. Okay? For a single k value, if you run it several times, unless it's clearly classifiable with that k value, it will differ. Right? That's something that you have to know. Okay, for the silhouette score, for large k value, it will become pretty close to 0, but in the beginning, it could fluctuate. So ideally, what you want to have is something that goes like this, 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 and then you would pick the highest one. Okay? Or even if it's highest, it might not be the right one, so you might have the next best one, something like that. But if that's not clearly visible, that could also be a problem. So, I mean, these are not so perfect, but you know what? At least it's unsupervised. You save money by not hiring people to do the labeling for you. Okay, and in many cases, you might not even be able to hire people. You might show the picture to somebody and say, "Hey, how many clusters do you see?" People might not see any clusters. So this unsupervised learning method could be actually more objective than using a human subject in cases of different data. Okay.